Subscribe so you don't miss out on any of these videos. The Sun is not only the center of our solar system but also the source of life as we know it on Earth. It is an enormous sphere of hot plasma, generating energy that powers everything from the smallest microorganisms to the most complex ecosystems. Its significance stretches beyond the realms of astronomy, impacting cultures, belief systems, and the very evolution of species. To understand the Sun, one must appreciate its physical characteristics, the processes that drive its behavior, and its profound influence on both Earth and the cosmos. At the most fundamental level, the Sun is a G-type main sequence star, or G-dwarf star. This places it in the middle of the stellar spectrum in terms of size, temperature, and brightness. It is far from the largest star in the universe, but to us, it is incomprehensibly massive. With a diameter of about 1.39 million kilometers, it could fit approximately 1.3 million Earths inside it. Its mass, accounting for more than 99% of the total mass of the solar system, is a staggering 330,000 times that of Earth. The energy the Sun emits is generated by nuclear fusion in its core. This process involves the fusion of hydrogen atoms into helium, releasing vast amounts of energy in the form of electromagnetic radiation. The energy created in the core takes thousands, even millions of years to reach the Sun's surface, where it is finally emitted into space. This energy travels to Earth in the form of sunlight, providing the warmth and light that sustain our planet's biosphere. The journey from the Sun to Earth, a distance of about 150 million kilometers, takes just over 8 minutes for sunlight to reach us, traveling at the speed of light. The Sun's structure is divided into several distinct layers, each playing a critical role in its overall functioning. At the core, when nuclear fusion occurs, the temperature reaches around 15 million degrees Celsius. Moving outward, the radiative zone surrounds the core, where energy is transferred by radiation. It takes photons an incredibly long time to pass through this dense region due to constant scattering. Beyond this, in the convective zone, energy is transferred by convection, with hot plasma rising and cooler plasma descending in circular patterns. At the surface of the Sun, known as the photosphere, temperatures drop to around 5,500 degrees Celsius, yet the Sun still appears incredibly bright to us. This is the part of the Sun we can see, a turbulent layer of roiling gases, marked by sunspots, cooler, darker areas caused by the Sun's magnetic field. These sunspots often indicate increased solar activity, such as solar flares or coronal mass ejections, CMEs, which can have significant effects on space weather and consequently, Earth's technological systems. Beyond the photosphere lies the chromosphere and the corona. The chromosphere is a thin layer above the photosphere that appears reddish during solar eclipses. It is home to spicules and prominences, jets and loops of solar material ejected into space. The corona, the Sun's outermost layer, extends millions of kilometers into space. Surprisingly, the corona is much hotter than the Sun's surface, with temperatures reaching over 1,000,000 degrees Celsius. The reason for this extreme heating remains one of the mysteries of solar physics, although scientists believe it is connected to magnetic reconnection and wave heating phenomena. The Sun's magnetic field is a powerful and dynamic force that shapes much of its behavior. It undergoes an 11-year cycle of activity, during which the magnetic poles flip, and the frequency of sunspots, flares, and CMEs fluctuates. During periods of high solar activity, the Sun emits more intense bursts of energy, which can affect Earth by disrupting satellite communications, power grids, and even creating spectacular auroras near the poles. Solar flares, in particular, are sudden bursts of electromagnetic radiation caused by the release of magnetic energy stored in the Sun's atmosphere. These flares can affect Earth's ionosphere, disrupting radio communications and GPS signals. Meanwhile, coronal mass ejections are massive clouds of solar plasma hurled into space by the Sun's magnetic field. If a CME collides with Earth's magnetosphere, it can trigger geomagnetic storms, which may have dramatic effects on power systems and cause widespread technological failures. Despite these occasional disruptions, the Sun is the cornerstone of life on Earth. Without its energy, our planet would be a frozen wasteland, incapable of sustaining life. The Sun drives the water cycle, powers photosynthesis in plants and regulates Earth's climate. It is also the reason for our day-night cycle, and its gradual variations in energy output have been linked to both short-term climate events and long-term shifts like ice ages. The sun's influence extends well beyond Earth. It is the gravitational anchor for the entire solar system, keeping planets, moons, asteroids, and comets in orbit. Its powerful solar wind, a stream of charged particles emanating from the corona, interacts with planetary atmospheres and magnetospheres, shaping the environment of space itself. The heliosphere, a bubble of solar wind that surrounds the solar system, protects us from much of the cosmic radiation that permeates the galaxy. Over billions of years, the sun's life cycle will unfold in a series of dramatic stages. Currently, it is about 4.6 billion years old, roughly halfway through its life. As the hydrogen in its core is gradually consumed, the sun will eventually begin to burn helium, causing it to expand into a red giant. During this phase, it will engulf the inner planets, including Earth, and its outer layers will drift into space, leaving behind a dense, hot core, a white dwarf. Over time, this remnant will cool and fade, leaving only a faint ghost of the star that once was. For humanity, the sun's long-term evolution poses both a challenge and a mystery. While it will take billions of years for the sun to reach the red giant phase, its gradual brightening over the next billion years will likely make Earth uninhabitable. As the sun ages, it will emit more energy, increasing surface temperatures on Earth and potentially evaporating the oceans. This timeline provides humanity with a distant, but inevitable, existential threat. In modern times, space missions have transformed our understanding of the sun. NASA's Parker Solar Probe, launched in 2018, is the closest any human-made object has ever come to the sun, gathering data about its outer atmosphere and the forces driving the solar wind. Other missions, like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, have provided detailed images and information about the sun's magnetic activity and surface phenomena. These efforts are crucial, not only for advancing solar physics but also for protecting Earth from the potential hazards of solar activity. The study of the sun also has implications for the search for life elsewhere in the universe. Stars like the sun, known as G-type stars, are relatively common in the Milky Way galaxy. Understanding how the sun formed, evolved, and nurtured life on Earth can help astronomers identify other stars and planetary systems where similar conditions might exist. In the hunt for exoplanets, scientists often focus on stars that are similar to the sun, as they are more likely to host planets within the habitable zone, where liquid water, and potentially life, could exist. The sun's ultimate role in human exploration of space is yet another intriguing aspect of its influence. As humanity begins to venture beyond Earth, understanding the sun and its behavior becomes increasingly important. Solar radiation poses significant challenges for long-term space travel, and future explorers will need to develop technologies to shield themselves from its harmful effects. At the same time, harnessing solar energy will be essential for powering space missions, colonies, and other endeavors beyond Earth. The harnessing of solar energy, even here on Earth, has already transformed the way we generate electricity and utilize renewable resources. Solar power, derived directly from the sun's rays, is one of the most promising forms of clean energy available today. Photovoltaic (PV) cells convert sunlight into electricity by taking advantage of the photoelectric effect, where photons knock electrons loose from atoms within a material, generating an electrical current. Solar panels composed of these PV cells are now a common sight in many parts of the world, providing an alternative to fossil fuels and reducing humanity's reliance on non-renewable energy sources. As solar technology advances, its efficiency and accessibility continue to improve. The widespread adoption of solar power has the potential to dramatically reduce greenhouse gas emissions and mitigate the effects of climate change. Beyond individual panels on rooftops, large-scale solar farms have been developed, capable of powering entire communities. Additionally, innovations like solar thermal energy, which uses mirrors to focus sunlight and generate heat, have opened up new possibilities for sustainable energy production. These technologies reflect humanity's deepening relationship with the sun, transforming its vast and consistent energy output into a resource for the future. The sun has also played a key role in human exploration, not only in the pursuit of knowledge about the solar system, but also in the navigation of the seas and the discovery of new lands. Before the invention of modern navigation tools, sailors relied heavily on the sun to determine their location and direction. The concept of latitude, the measure of distance from the equator, was derived from the angle of the sun above the horizon at noon. This knowledge allowed ancient explorers to travel vast distances, opening up new frontiers and expanding the reach of human civilization. As we move into the modern era, the sun continues to inspire awe and curiosity. Solar eclipses, in particular, remain one of the most visually striking and scientifically valuable celestial events. During a solar eclipse, the moon passes between the Earth and the sun, temporarily blocking the sun's light and casting a shadow over parts of the Earth. These events, though brief, provide a rare opportunity for scientists to study the sun's outer layers, including the corona, which is usually obscured by the brightness of the sun's surface. Despite all that we know about the sun, there is still much that remains a mystery. For instance, the sun's corona, as mentioned earlier, is much hotter than its surface, an enigma that has puzzled scientists for decades. Various theories have been proposed to explain this phenomenon, including the possibility that magnetic waves or nanoflares contribute to the extreme temperatures, but the exact mechanism remains uncertain. Additionally, the sun's magnetic field is complex and poorly understood, particularly the processes that cause its poles to flip every 11 years and drive the solar cycle of activity. Another mystery lies in the sun's future. While we know that it will eventually expand into a red giant, and then shrink into a white dwarf, the finer details of this process are still being studied. The interactions between the dying sun and the planets that survive its transformation are a subject of intense research, with scientists eager to learn more about how planetary systems evolve around aging stars. This knowledge is crucial, not only for understanding the fate of our solar system but also for interpreting the life cycles of exoplanetary systems across the galaxy. In recent years, the field of heliophysics, the study of the sun and its influence on the solar system, has become increasingly important. As our reliance on technology grows, so too does our vulnerability to space weather caused by solar activity. Geomagnetic storms, triggered by solar flares and CMEs, can disrupt satellites, communications, and power grids, posing a significant risk to modern infrastructure. Understanding and predicting solar activity has become a priority for space agencies and governments worldwide, with the aim of mitigating the potential impacts of solar storms on Earth. The sun's role in shaping Earth's climate is another area of active investigation. While the primary driver of climate change is human activity, particularly the burning of fossil fuels, natural variations in the sun's energy output can also influence global temperatures. The sun's energy output is not constant. It fluctuates slightly over time due to the solar cycle and other factors. These variations, combined with volcanic activity and other natural phenomena, have contributed to past climate events such as the Little Ice Age, a period of cooling that occurred between the 14th and 19th centuries. Understanding the sun's influence on climate is essential for accurately modeling future climate scenarios and preparing for potential changes in Earth's environment. While the sun is not the primary cause of current global warming, its interactions with Earth's atmosphere, oceans, and magnetic field play a role in shaping long-term climate trends. Solar research, therefore, is a critical component of both astronomy and environmental science, bridging the gap between space exploration and the study of life on Earth. The sun's influence on Earth's climate extends far beyond just its energy output. The interactions between solar radiation and Earth's atmosphere, particularly the way sunlight is absorbed, reflected, and re-radiated, are crucial factors in understanding weather patterns and long-term climate behavior. The balance between incoming solar radiation and outgoing heat energy is what maintains Earth's average temperature, often referred to as Earth's energy budget. Any changes in this balance, whether from fluctuations in solar activity, greenhouse gases, or other factors, can lead to significant shifts in climate. While greenhouse gases trap heat within Earth's atmosphere, solar energy is the driving force behind the planet's weather systems. The uneven heating of Earth's surface due to the tilt of its axis causes air and ocean currents to circulate, distributing heat across the globe. The sun's energy powers phenomena like the trade winds, jet streams, and monsoon systems, all of which have profound effects on global weather. Seasonal variations, driven by Earth's orbit around the sun, further influence these patterns, creating the cyclical changes we experience throughout the year. The study of solar-terrestrial interactions is an interdisciplinary field, combining aspects of meteorology, oceanography, and space science. Researchers in this field seek to understand how the sun's varying energy output influences weather and climate on different timescales, from daily weather patterns to multi-decade shifts like El Niño and La Niña. These periodic changes in sea surface temperatures in the Pacific Ocean, for example, are closely tied to variations in solar heating and have wide-ranging effects on global weather, including droughts, floods, and temperature anomalies. Another aspect of solar-terrestrial interaction is the role of the sun in the formation and behavior of Earth's magnetic field. The Earth is surrounded by a protective magnetic field, generated by the movement of molten iron in its outer core. This magnetic field shields the planet from much of the sun's harmful radiation, including solar wind, a stream of charged particles continuously emitted by the sun. However, during periods of intense solar activity, such as solar flares or coronal mass ejections, CMEs, the solar wind can intensify, causing geomagnetic storms that interact with Earth's magnetic field. These geomagnetic storms can produce spectacular displays of the auroras, better known as the northern and southern lights, as solar particles collide with gases in Earth's upper atmosphere. While these displays are beautiful, the storms themselves can be disruptive. Strong geomagnetic storms can interfere with satellite communications, GPS systems, and even cause power grid failures. One of the most significant historical examples of this occurred in 1859 during the Carrington event, a massive solar storm that knocked out telegraph systems and produced auroras visible as far south as the Caribbean. Since then, humanity's technological infrastructure has become far more advanced and far more vulnerable to space weather. Satellites, telecommunications networks, and even air travel can be impacted by high levels of solar radiation and geomagnetic disturbances. The possibility of another major solar storm, comparable to the Carrington event, is a genuine concern for governments and scientists around the world. Monitoring the sun for signs of impending solar storms and developing strategies to protect critical infrastructure are important components of space weather forecasting. Space weather forecasting relies on a network of satellites and ground-based observatories that continuously monitor the sun's activity. Instruments aboard these spacecraft measure the intensity of solar radiation, the speed and composition of solar wind, and the sun's magnetic field. These observations allow scientists to predict when a solar flare or CME is likely to impact Earth and issue warnings to industries that could be affected. While we cannot prevent solar storms, this advanced warning system can help mitigate their effects, ensuring that satellites are placed into safe modes and power grids are protected from potential damage. The connection between the Sun and Earth's magnetic field also raises interesting questions about the possibility of space exploration beyond Earth's protective magnetic shield. In space, astronauts and spacecraft are exposed to much higher levels of radiation from both the Sun and cosmic rays, which originate from beyond the solar system. Protecting humans and equipment from this radiation is one of the greatest challenges for long-term space missions, such as a journey to Mars. Spacecraft need to be shielded from solar radiation, and astronauts must have ways to protect themselves during solar storms. On Earth, we are fortunate to have both the magnetic field and the atmosphere to protect us from most of the Sun's harmful radiation. The ozone layer in Earth's stratosphere absorbs the majority of the Sun's ultraviolet, UV, radiation, preventing it from reaching the surface. Without this protective layer, life on Earth would be exposed to dangerous levels of UV radiation, which can damage DNA and lead to increased rates of skin cancer and other health issues. This is one reason why the depletion of the ozone layer, caused by human-made chemicals like chlorofluorocarbons, CFCs, became a major environmental concern in the late 20th century. The Montreal Protocol, an international treaty signed in 1987, successfully phased out the production and use of many ozone-depleting substances, leading to a gradual recovery of the ozone layer. This is a rare success story in environmental science and international cooperation, demonstrating the importance of protecting Earth's atmosphere from human-caused damage. It also underscores the sun's role in shaping life on Earth, both as a source of energy and as a potential threat if its radiation is not properly mitigated. The sun's importance to life on Earth cannot be overstated. Beyond providing the energy necessary for photosynthesis, the sun's light and warmth are essential for maintaining the conditions that support life. The habitable zone, or the Goldilocks zone, around a star is the region where conditions are just right for liquid water to exist on the surface of a planet. Earth sits comfortably within the sun's habitable zone, a fortunate alignment that has allowed life to flourish for billions of years. However, the sun's role in the potential habitability of other worlds extends beyond our solar system. The discovery of exoplanets, planets that orbit stars outside our solar system, has revealed that many stars have their own habitable zones. Scientists are particularly interested in stars similar to the Sun, known as G-type main sequence stars, as they are more likely to host planets with conditions suitable for life. The study of exoplanetary systems and their stars is a rapidly growing field, with the hope that we might one day discover life beyond Earth. Even within our own solar system, the Sun's influence is crucial to understanding the habitability of nearby worlds. For example, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are thought to have subsurface oceans of liquid water, heated not by sunlight but by tidal forces generated by their orbits around their host planets. These moons are some of the most promising candidates for finding extraterrestrial life within the solar system, and future missions to explore them will rely on solar power to operate in the outer reaches of the solar system. The future of solar exploration promises exciting new discoveries and technologies. The ongoing Parker Solar Probe mission, launched in 2018, is designed to study the Sun's outer atmosphere by flying closer to the Sun than any spacecraft has before. Its findings are expected to shed light on some of the Sun's most enduring mysteries, including the high temperatures of the corona and the origins of the solar wind. This mission represents humanity's closest approach to the Sun, a daring attempt to unravel the secrets of our closest star. The Parker Solar Probe is a testament to both the technological advancements and the insatiable curiosity that drive humanity's exploration of the Sun. By venturing into the Sun's outer atmosphere, the spacecraft encounters extreme temperatures and radiation levels that would be fatal to any unshielded object. To survive these harsh conditions, the probe is equipped with a cutting-edge heat shield, designed to withstand temperatures of up to 2,500 degrees Fahrenheit, 1,377 degrees Celsius. This shield allows the Parker Solar Probe to pass through the Sun's corona while collecting invaluable data on its magnetic fields, solar winds, and energetic particles. One of the primary goals of the Parker Solar Probe mission is to better understand the origins of the solar wind, a stream of charged particles that flows outward from the Sun and permeates the entire solar system. These particles interact with the planets and can have significant effects on space weather. By getting closer to the Sun than ever before, the probe aims to determine the precise mechanisms that accelerate the solar wind and drive its movement. This information is vital not only for understanding the Sun's behavior but also for protecting Earth's technological infrastructure from the potential disruptions caused by space weather. The study of the solar wind also has implications for future space travel. As humans set their sights on deep space exploration, including missions to Mars and beyond, understanding and mitigating the effects of solar radiation will be crucial for ensuring the safety of astronauts. Solar winds, along with cosmic rays, represent a major source of radiation in space, and prolonged exposure can pose serious health risks. Developing effective shielding technologies and predicting solar events will be essential for the success of long-duration missions, such as those proposed for the colonization of Mars. In addition to the Parker Solar Probe, another groundbreaking mission studying the Sun is the Solar Orbiter, launched by the European Space Agency, ESA, in collaboration with NASA. The Solar Orbiter is designed to capture unprecedented images of the Sun's poles, providing new insights into the solar cycle and its magnetic field dynamics. The spacecraft's unique orbit allows it to study parts of the Sun that have been difficult to observe in the past, including the poles, which play a key role in the generation of the Sun's magnetic activity. One of the most fascinating aspects of the solar orbiter's mission is its potential to help scientists understand the solar dynamo, the process by which the Sun generates its magnetic field. The Sun's magnetic field is responsible for many of its most dramatic behaviors, including sunspots, solar flares, and CMEs. These phenomena are all linked to the solar cycle, an approximately 11-year period during which the Sun's magnetic field becomes increasingly active, peaks, and then reverses polarity. By studying the solar poles, scientists hope to uncover new information about how the solar dynamo works and how it influences the entire solar system. The relationship between the Sun's magnetic field and sunspot activity is another area of ongoing research. Sunspots are dark, cooler regions on the Sun's surface where the magnetic field is particularly strong. They are often precursors to solar flares and CMEs, both of which can have significant impacts on space weather. During periods of high sunspot activity, known as solar maximum, the Sun is more likely to produce these intense bursts of energy. Conversely, during solar minimum, when sunspots are scarce, the Sun's activity is generally lower. Understanding the causes of these cycles and how they affect the Earth remains a central focus of solar research. In recent years, scientists have made significant strides in predicting solar flares and CMEs. By closely monitoring the Sun's surface and magnetic field, space weather forecasters can issue warnings when they detect signs of an impending solar event. This early warning system is critical for protecting satellites, power grids, and other infrastructure from the potentially damaging effects of a strong solar storm. However, predicting the exact timing and intensity of these events remains a challenge, and more research is needed to improve the accuracy of space weather forecasts. The connection between solar activity and space weather extends beyond just the Earth. Other planets in the solar system, as well as their moons, are also affected by the Sun's behavior. For example, Mars, which lacks a global magnetic field, is particularly vulnerable to solar radiation. The thin Martian atmosphere offers little protection from the solar wind, and during periods of intense solar activity, the planet can lose significant amounts of its atmospheric gases. This process is thought to have contributed to the thinning of Mars's atmosphere over billions of years, transforming it from a once potentially habitable planet into the cold, arid world we see today. Similarly, the gas giant planets, Jupiter, Saturn, Uranus, and Neptune, experience their own unique interactions with the Sun's energy. These planets have strong magnetic fields, but their atmospheres and magnetospheres respond differently to solar activity compared to Earth. For instance, Jupiter's immense magnetic field creates powerful auroras at its poles, similar to the northern and southern lights on Earth but on a much grander scale. These auroras are influenced not only by the solar wind but also by the planet's own internal processes and interactions with its moons, particularly Io, which is volcanically active. Studying how the Sun affects the entire solar system, from the inner rocky planets to the outer gas giants, provides valuable insights into both the dynamics of the solar system and the behavior of other star systems. Many of the principles that govern the interactions between the Sun and its planets can be applied to exoplanetary systems, helping scientists better understand the potential habitability of planets orbiting distant stars. The more we learn about our own Sun, the better we can interpret the conditions around other stars and assess whether they might support life. The Sun's influence also extends to the very edge of the solar system, where the solar wind interacts with the interstellar medium, the region of space between star systems. This boundary, known as the heliopause, marks the point at which the Sun's influence weakens, and the environment is dominated by material from outside the solar system. In 2012, NASA's Voyager 1 spacecraft became the first human-made object to cross the heliopause and enter interstellar space, providing unprecedented data on this remote region. The exploration of the outer solar system and beyond has revealed just how far-reaching the Sun's influence truly is. Even at the distant reaches of the solar system, where sunlight is weak, the Sun's gravitational pull continues to shape the orbits of comets, dwarf planets, and other small bodies. These objects, often referred to as the frozen relics of the early solar system, provide clues about the formation of the Sun and its planets. By studying them, scientists hope to piece together the history of the solar system and understand how it evolved over billions of years. The study of comets, in particular, has yielded fascinating insights into the early solar system. Comets are composed of ice, dust, and rocky material, and they are thought to have formed in the outer regions of the solar system, far from the Sun's heat. As comets approach the Sun, their icy surfaces begin to vaporize, creating the characteristic tails that we associate with these celestial objects. The material in these tails is a direct sample of the early solar system, preserved in a frozen state for billions of years. In recent years, missions like the European Space Agency's Rosetta spacecraft have provided a wealth of information about comets and their composition. By landing a probe on the surface of Comet 67P/Churyumov-Gerasimenko, the Rosetta mission was able to analyze the chemical makeup of the comet's surface and investigate the role that comets may have played in delivering water and organic molecules to Earth. These findings have implications for understanding how life may have originated on our planet, and whether similar processes could occur elsewhere in the universe. As we continue to study the Sun and its interactions with the solar system, new questions and mysteries inevitably arise. The Sun, for all that we have learned about it, remains a dynamic and unpredictable star. Its cycles of activity, its influence on space weather, and its role in the habitability of planets both near and far are topics that will continue to captivate scientists for generations to come. The Sun's potential to influence life on Earth, and its ability to shape the conditions for habitability in other parts of the solar system is an essential area of study. It raises questions about the long-term future of both our planet and humanity as a species. While the Sun currently provides the energy that sustains life on Earth, it will not remain in its present state forever. Like all stars, the Sun is in a constant state of evolution, and understanding its future is crucial for predicting the fate of the solar system. The Sun is currently in the middle of its main sequence phase, during which it fuses hydrogen into helium in its core. This phase has lasted for approximately 4.6 billion years and will continue for several billion more. However, as the Sun ages, it will eventually exhaust the hydrogen in its core, marking the end of the main sequence. At this point, the Sun will undergo dramatic changes, transitioning into the next phase of its stellar evolution, becoming a red giant. As the Sun becomes a red giant, it will expand dramatically, engulfing the inner planets of the solar system, including Mercury and Venus. It is uncertain whether Earth will be swallowed by the expanding Sun, but even if it escapes direct engulfment, the planet will become uninhabitable. The Sun's increased luminosity during this phase will cause Earth's oceans to evaporate, and its atmosphere will be stripped away. Any remaining life will face extreme conditions, with surface temperatures rising to levels that will likely make Earth a scorched and barren world. The red giant phase will be a relatively short-lived period in the Sun's life, lasting only a few 100 million years. During this time, the Sun will lose a significant amount of its mass through powerful solar winds. As the outer layers of the Sun are blown off into space, they will form a beautiful shell of gas and dust known as a planetary nebula. The core of the Sun, now exposed and no longer undergoing nuclear fusion, will cool and contract, eventually becoming a white dwarf. A white dwarf is the remnant of a star that has exhausted its nuclear fuel. It is incredibly dense, with a mass comparable to that of the Sun but compressed into a volume about the size of Earth. Although white dwarfs no longer undergo fusion reactions, they continue to emit heat and light for billions of years as they gradually cool. Over time, the white dwarf that was once the Sun will fade into a cold, dark object known as a black dwarf, essentially a dead star. The transformation of the Sun into a white dwarf, and eventually, a black dwarf marks the final stage in its evolution. However, this process will take place over billions of years, long after humanity will have had to find a way to survive the Sun's earlier expansion into a red giant. The fate of Earth and the other planets during this transformation will depend on a variety of factors, including the Sun's mass loss and the gravitational effects of neighboring stars. In the distant future, as the Sun evolves through these stages, the solar system as we know it will change dramatically. The outer planets, Jupiter, Saturn, Uranus, and Neptune, may survive the Sun's red giant phase, but their moons and the small icy bodies in the outer solar system will experience changes as the Sun's energy output diminishes. These regions, which currently lie far from the Sun's warmth, may temporarily experience higher temperatures, potentially triggering changes in their atmospheres and surfaces. The future of the solar system and its planets, especially Earth, is deeply connected to the Sun's life cycle. While these events will occur on timescales far beyond the human lifespan, they offer a glimpse into the long-term evolution of planetary systems. Moreover, understanding the Sun's life cycle helps scientists study the behavior of other stars and exoplanetary systems in various stages of development. The Sun's eventual transformation into a red giant, and later into a white dwarf, has profound implications for the search for habitable planets and other star systems. Studying the evolution of our own Sun provides clues about the fate of planets orbiting other stars and offers insights into where and when life might emerge in the universe. Stars of different masses and compositions evolve at different rates, and their ability to support life on surrounding planets depends on these evolutionary processes. The Sun is classified as a G-type main sequence star, or G-dwarf, but stars come in a wide range of sizes and types. Larger stars, such as O-type and B-type stars, burn through their fuel much more quickly than the Sun and have much shorter lifespans, often ending in spectacular supernova explosions. Smaller stars, such as M-type red dwarfs, have much longer lifespans and burn more slowly. Red dwarfs are the most common type of star in the galaxy, and their long lifetimes make them intriguing candidates for hosting habitable planets. However, red dwarfs also present challenges for habitability. They are known for emitting powerful solar flares that could strip the atmospheres of nearby planets, or bombard their surfaces with harmful radiation. This raises important questions about whether life could survive in such harsh environments. Understanding how stars like the Sun influence their planets helps scientists evaluate the potential for life around other types of stars and informs the ongoing search for extraterrestrial life. The study of exoplanets, planets that orbit stars other than the Sun, has become one of the most exciting fields of astronomy in recent years. With the discovery of thousands of exoplanets, including many in the so-called habitable zone, where conditions might be right for liquid water to exist, scientists are increasingly focused on identifying planets that could potentially support life. The Sun serves as a crucial reference point for these studies, as it provides a model for understanding the conditions necessary for habitability. In many ways, the Sun is an ordinary star, similar to countless others in the galaxy. Yet, its stability and relative calm have been critical for the development and sustenance of life on Earth. Unlike more massive stars that experience violent outbursts or frequent eruptions, the Sun has provided a consistent environment for billions of years, allowing life to evolve and flourish. This stability, combined with the presence of a magnetic field that shields Earth from harmful solar radiation, has been essential for the planet's habitability. The relationship between the Sun and Earth is a delicate balance, and even small changes in the Sun's behavior can have significant effects on the planet. As we continue to explore the intricacies of this relationship, we gain a deeper appreciation for the factors that make life possible, not just on Earth, but potentially elsewhere in the universe. The Sun, as the center of our solar system, remains the key to understanding these mysteries and unlocking the secrets of the cosmos. While we have made great strides in our understanding of the Sun and its effects, much remains to be discovered. The future of solar research holds the promise of even greater revelations, from the nature of the Sun's magnetic field to the intricacies of its internal structure. As new technologies and missions are developed, scientists will continue to push the boundaries of what we know about our star, providing new insights that could shape the future of humanity's exploration of space. The Sun's story is one of immense power, complexity, and beauty. It has shaped the solar system from its very beginning and will continue to influence its fate for billions of years to come. The study of the Sun is not just about understanding the physical processes that drive its behavior. It is also about exploring our place in the universe and the profound connections between the cosmos and life itself. The Sun's central role in shaping life on Earth cannot be overstated. It is the source of the energy that fuels nearly every process on our planet, from the simplest chemical reactions to the most complex ecosystems. Without the sun, Earth would be a cold, lifeless world, devoid of the conditions necessary to sustain life. It is no exaggeration to say that the sun's energy has been the foundation for life's emergence and evolution on our planet. At the heart of this relationship is photosynthesis, the process by which plants, algae, and some bacteria convert sunlight into chemical energy. Photosynthesis is the basis for nearly all life on Earth. It not only provides food for herbivores and indirectly for carnivores, but it also produces the oxygen that makes Earth's atmosphere breathable. Through photosynthesis, plants absorb carbon dioxide and release oxygen, creating a cycle that sustains the planet's life-supporting atmosphere. This delicate balance between photosynthesis and respiration has helped maintain the stability of Earth's climate and ecosystems for millions of years. The sun's light, absorbed by chlorophyll in plants, drives this process, converting solar energy into a form that can be stored and used by living organisms. Without this mechanism, life on Earth, as we know it, would not be possible. The sun's influence extends beyond biology. It also plays a critical role in shaping Earth's climate and weather patterns. The energy from the sun heats the Earth's surface, driving the circulation of the atmosphere and oceans. Differences in temperature between the equator and the poles create pressure gradients that lead to the movement of air and the formation of winds, storms, and ocean currents. These processes distribute heat around the planet, creating the diverse climates and environments that support life. Over geological time, variations in the sun's energy output have contributed to climate changes on Earth, including ice ages and warm periods. While these changes are typically slow and gradual, they have had profound effects on life and the planet's environment. The sun's energy is also responsible for phenomena such as the water cycle, in which water evaporates from the surface, forms clouds, and returns to Earth as precipitation, sustaining ecosystems and agriculture. The sun's impact on Earth is not limited to its light and heat. The solar wind, a stream of charged particles constantly emitted by the sun, interacts with Earth's magnetic field, creating the auroras that light up the polar skies. These spectacular displays of light occur when solar particles collide with atoms in Earth's atmosphere, releasing energy in the form of colorful lights. The auroras, commonly known as the northern and southern lights, are visible in regions near the poles and serve as a reminder of the sun's powerful influence on our planet. While the solar wind is mostly harmless, large solar storms, or coronal mass ejections, CMEs, can cause disruptions on Earth. These massive bursts of solar energy can affect satellites, communication systems, and even power grids. The study of space weather, which examines how solar activity affects Earth's environment, is a growing field of research. As society becomes increasingly reliant on technology, understanding and predicting solar storms will become even more important for protecting our infrastructure. One of the most intriguing aspects of the sun is its magnetic activity, which drives many of its most dramatic phenomena, such as sunspots, solar flares, and CMEs. The sun's magnetic field is generated by the movement of plasma in its interior. This magnetic field is not static but constantly changes and evolves, leading to cycles of increased and decreased solar activity. The most well-known of these cycles is the 11-year solar cycle, during which the number of sunspots on the sun's surface rises and falls. Sunspots are regions of intense magnetic activity that appear darker than their surroundings because they are cooler. These spots are often associated with solar flares, powerful bursts of energy that can release as much energy as billions of nuclear bombs. Solar flares can send streams of charged particles into space, sometimes hitting Earth and affecting communication systems and power grids. Understanding the sun's magnetic activity is crucial for predicting these events and mitigating their potential impacts. The sun's magnetic field also extends far beyond the solar system, creating the heliosphere, a bubble of charged particles that surrounds the solar system and acts as a shield against cosmic rays from other parts of the galaxy. The heliosphere plays a crucial role in protecting the solar system from high-energy particles that could be harmful to life. However, as the sun's magnetic activity fluctuates, so does the strength of the heliosphere, influencing the amount of cosmic radiation that reaches Earth. The study of the sun's magnetic field and its interactions with the rest of the solar system is key to understanding not only the sun's behavior but also its broader impact on space weather and the environment of the solar system. It also provides insights into the nature of other stars and their magnetic activity. By studying our sun, scientists can develop models that help explain the behavior of distant stars and the environments of their surrounding planets. As we look toward the future, one of the most exciting frontiers in solar research is the study of the sun's interior. Although we cannot see inside the sun directly, scientists use a technique called helioseismology to study the sun's inner layers. By analyzing the vibrations and oscillations on the sun's surface, researchers can infer what is happening beneath the surface, much like seismologists use earthquake waves to study Earth's interior. Helioseismology has revealed that the sun's interior is composed of several distinct layers, each with different physical properties. At the core, nuclear fusion generates the energy that powers the sun. This energy is transported outward through the radiative zone, where it takes thousands of years for energy to move from the core to the outer layers. Finally, in the convective zone, energy is transported by the movement of hot plasma, which rises to the surface, cools, and then sinks again in a process called convection. The study of the sun's interior is crucial for understanding how stars produce and transport energy. It also provides insights into the long-term stability of the sun and its ability to continue providing the energy necessary for life on Earth. As technology advances, new methods for probing the sun's interior will allow scientists to unlock even more of the sun's secrets. The sun's influence on Earth and the solar system is immense, but it also plays a key role in the broader context of the galaxy. As a middle-aged star, the sun is one of billions in the Milky Way galaxy. Its formation and evolution provide clues about the formation of other planetary systems and the potential for life elsewhere in the universe. The sun's relatively calm and stable nature has allowed life to flourish on Earth, but not all stars are so hospitable. Many stars are much more active than the sun, producing frequent and violent flares that could be devastating to any planets orbiting them. Other stars are much cooler and less luminous, creating challenges for the development of life. By studying the sun, scientists gain valuable insights into the conditions that are necessary for habitability and the likelihood of life in other parts of the galaxy. The sun is not just a source of light and energy, it is also a laboratory for studying fundamental physics. The extreme temperatures and pressures inside the sun provide an environment that cannot be replicated on Earth. Studying the sun allows scientists to test theories about the behavior of matter under extreme conditions and to explore the fundamental forces of nature, such as gravity, electromagnetism, and nuclear forces. In addition, the sun's constant output of energy makes it a key player in the search for alternative energy sources. Solar power is one of the most promising renewable energy technologies, harnessing the sun's energy to generate electricity without producing harmful emissions. As the world grapples with the challenges of climate change and the need to transition to cleaner energy sources, solar power offers a sustainable solution that could play a major role in reducing humanity's reliance on fossil fuels. The potential of solar energy is immense. Every hour, the Earth receives more energy from the sun than the entire human population consumes in a year. If humanity could capture just a fraction of that energy efficiently, it could meet global energy demands many times over. Solar panels, which convert sunlight into electricity using photovoltaic cells, are becoming increasingly efficient and affordable, making solar energy one of the fastest-growing sources of renewable power. The development of solar energy technology has led to innovations not only in energy generation but also in energy storage. Since the sun does not shine 24 hours a day, storing solar energy for use during the night or on cloudy days is a crucial part of making solar power a reliable energy source. Advances in battery technology and other energy storage methods are helping to overcome this challenge, making solar power a more viable option for both individuals and large-scale energy grids. In addition to providing electricity, solar energy can also be used for heating and cooling. Solar thermal systems capture the sun's heat to provide hot water, space heating, or even to generate electricity through concentrated solar power, CSP. These systems can be used in a variety of settings, from homes and businesses to large power plants that supply electricity to entire cities. The sun's energy is also being explored as a means of powering space exploration. Solar panels are commonly used on spacecraft to provide power for long missions. As humanity looks to expand its presence beyond Earth, solar energy could play a key role in sustaining life and powering missions to the Moon, Mars, and beyond. Future spacecraft and space habitats may rely on solar power as a primary source of energy, reducing the need for resupply missions and enabling longer stays in space. The sun's potential to drive innovation and progress extends beyond energy production. It also plays a critical role in climate science, as understanding the sun's influence on Earth's climate is essential for predicting and mitigating the effects of climate change. While human activities are the primary driver of current global warming, natural variations in solar output can also affect Earth's climate. By studying past solar cycles and their impacts on the climate, scientists can improve models that predict future climate changes. One of the major challenges in understanding the sun's role in climate is the complex interaction between solar radiation, the atmosphere, and Earth's surface. The sun's energy is not evenly distributed across the planet, and factors such as cloud cover, ice reflectivity, and atmospheric composition all influence how much solar energy reaches the surface and how it is absorbed or reflected back into space. These interactions are further complicated by feedback loops, such as the melting of polar ice, which reduces Earth's reflectivity and causes more solar energy to be absorbed, accelerating warming. As researchers work to untangle these complexities, new technologies and methods are being developed to monitor the sun and its interactions with Earth in greater detail. Satellites equipped with instruments to measure solar radiation, atmospheric composition, and surface temperature are providing valuable data that helps scientists refine their understanding of the sun's role in the climate system. This knowledge is critical not only for addressing the immediate challenges of climate change, but also for planning for the long-term future of humanity on Earth. The sun's future, however, is not without its challenges. Like all stars, the sun is not eternal. It is currently in the middle of its life cycle, but eventually it will exhaust the supply of hydrogen fuel in its core and undergo significant changes. When the sun's hydrogen is depleted, it will enter the red giant phase, expanding dramatically as it begins to fuse helium. During this phase, the sun will grow so large that it may engulf the inner planets, including Earth. While this transformation is billions of years away, it represents a critical moment in the history of the solar system. As the sun swells into a red giant, the intense heat and radiation will render Earth uninhabitable long before the planet is consumed. The oceans will evaporate, the atmosphere will be stripped away, and any remaining life will be extinguished. This future scenario is a reminder of the fragility of life and the need for humanity to explore options for survival beyond Earth. The final stage of the sun's life will occur when it sheds its outer layers, leaving behind a dense core known as a white dwarf. This remnant will gradually cool and fade over billions of years, no longer producing energy through nuclear fusion. The sun's white dwarf stage marks the end of its life as an active star, but it will remain a part of the galaxy for a long time to come, slowly cooling and dimming until it becomes a cold, dark object. The eventual death of the sun raises profound questions about the long-term fate of life in the universe. As stars like the sun age and die, the environments that support life on their planets will also change. If humanity survives long enough to witness the sun's transformation into a red giant, it may need to seek refuge elsewhere in the galaxy, possibly around a younger star or in a more stable part of the universe. The study of other stars and planetary systems is critical to understanding the potential for life beyond Earth and preparing for the distant future when the sun is no longer a viable home. While the end of the sun's life is far in the future, its study continues to provide valuable insights into the nature of stars and the broader universe. One of the most exciting areas of research is the search for exoplanets, planets orbiting other stars. By studying the sun and its interactions with Earth, scientists have developed tools and techniques for detecting and analyzing exoplanets, many of which may lie in the habitable zones of their parent stars, where conditions are suitable for life. The discovery of exoplanets has revolutionized our understanding of the universe, and raise the possibility that life may exist elsewhere. Some exoplanets orbit stars similar to the Sun, while others orbit stars that are much larger, smaller, or more active. Each of these planetary systems offers new opportunities for learning about the diversity of worlds in the universe and the potential for life beyond our solar system. The Sun, as an average star in the Milky Way galaxy, serves as a reference point for understanding other stars and their planetary systems. By studying the Sun's life cycle, magnetic activity, and interactions with Earth, scientists can develop models that apply to other stars and their planets. This research is critical for assessing the habitability of exoplanets and the potential for discovering life elsewhere in the galaxy. In many ways, the Sun is a microcosm of the universe itself. Its life cycle, from formation to eventual death, mirrors the processes that occur in stars across the galaxy. Its energy drives the processes that sustain life on Earth, while its magnetic activity shapes the environment of the entire solar system. The Sun's interactions with other stars, planets, and cosmic phenomena offer a glimpse into the broader workings of the cosmos. The Sun's study is far from complete, and new discoveries about its nature are being made all the time. From its dynamic surface to its mysterious core, the Sun continues to challenge our understanding of the universe and our place within it. Advances in technology, such as new solar observatories and space missions, will allow scientists to explore the Sun in unprecedented detail, unlocking new secrets about the star that has shaped life on Earth for billions of years. As we continue to learn more about the Sun, we gain not only a deeper appreciation for its role in our lives but also a greater understanding of the fundamental forces that govern the universe. The Sun, in all its complexity and power, remains a source of wonder and inspiration, reminding us of the vastness of the cosmos and the incredible processes that sustain life on our small, fragile planet. As we advance technologically and scientifically, the Sun remains at the center of our exploration of energy, climate, and the fundamental laws of nature. It has become a focal point for discussions about sustainability and the future of our planet. The transition from fossil fuels to renewable energy sources is crucial for combating climate change, and solar energy stands out as one of the most promising alternatives. This shift represents not just an environmental necessity, but also a moral imperative to protect the planet for future generations. Moreover, the development of solar technology fosters international collaboration. Countries around the world are investing in solar energy research and infrastructure, sharing knowledge and resources to harness the Sun's power more effectively. This global effort underscores the recognition that climate change and energy sustainability are challenges that transcend borders. As nations work together to combat these issues, the Sun serves as a common thread, uniting humanity in the quest for a more sustainable future. The advances in solar technology are complemented by public awareness and advocacy for renewable energy. Grassroots movements, environmental organizations, and educational initiatives are spreading knowledge about the benefits of solar power and promoting its adoption in communities worldwide. This increasing awareness is critical for fostering a culture that values sustainability and prioritizes clean energy solutions. Yet, while the promise of solar energy is bright, there are also challenges that must be addressed. The production of solar panels, for instance, involves resource extraction and manufacturing processes that can have environmental impacts. Finding sustainable methods to produce solar technology is essential to ensuring that the transition to solar energy is truly beneficial for the planet. Additionally, the integration of solar power into existing energy grids poses technical and logistical challenges that require innovative solutions. In the context of climate change, the Sun's energy presents both opportunities and challenges. While the increasing concentration of greenhouse gases in the atmosphere is driving global warming, solar energy offers a path toward reducing emissions and mitigating climate change's impacts. However, the effects of climate change can also influence solar energy production. For instance, extreme weather events, shifts in precipitation patterns, and changes in temperature can affect the efficiency and reliability of solar power systems. The Sun's influence on Earth's climate extends beyond the immediate effects of solar radiation. Solar cycles, which are approximately 11 years long, can also impact weather patterns and climate over longer timescales. Understanding these cycles and their interactions with other climatic factors is critical for developing accurate climate models and predicting future conditions. This knowledge is essential for informing climate policy and planning for the impacts of climate change on ecosystems and human societies. In addition to its role in energy and climate, the Sun is a key player in the field of astrophysics. Studying the Sun helps scientists understand stellar processes and the life cycles of other stars in the universe. The insights gained from solar research inform our understanding of stellar evolution, magnetic activity, and the dynamics of celestial bodies. The Sun serves as a valuable laboratory for astrophysical phenomena, enabling researchers to test theories and refine models that apply to a wide range of stars. As technology advances, our ability to observe and study the Sun improves dramatically. Satellite missions like the Solar Dynamics Observatory, SDO, and the Parker Solar Probe are revolutionizing our understanding of the Sun's behavior and its impact on the solar system. These missions provide unprecedented data on solar flares, coronal mass ejections, and the solar wind, deepening our understanding of how the Sun influences not only Earth but also the entire solar system. The Solar Dynamics Observatory, launched in 2010, continuously observes the Sun in various wavelengths, capturing high-resolution images of solar activity. Its findings have led to groundbreaking insights into the mechanisms behind solar eruptions and the intricate magnetic fields that govern the Sun's behavior. Meanwhile, the Parker Solar Probe, which was launched in 2018, is the first spacecraft to fly into the Sun's outer atmosphere, or corona, allowing scientists to gather data on solar phenomena in ways previously thought impossible. Through these and other missions, researchers are uncovering the complex dynamics of the Sun, such as how magnetic fields generate solar activity, and how this activity impacts space weather. Space weather, driven by solar eruptions and the solar wind, can have significant effects on satellite communications, navigation systems, and even power grids on Earth. Understanding the Sun's behavior is critical for predicting and mitigating the impacts of space weather on modern technology and infrastructure. The pursuit of knowledge about the Sun extends beyond scientific inquiry. It is also a testament to humanity's curiosity and desire to explore the unknown. The quest to understand the Sun reflects our innate drive to seek answers to fundamental questions about the universe and our place within it. As we delve deeper into the mysteries of the Sun, we are not only expanding our scientific knowledge but also connecting with something greater, a shared exploration of the cosmos. This exploration invites us to reflect on our responsibilities as stewards of the Earth and its resources. The Sun, as a powerful source of energy, reminds us of the importance of sustainable practices and the need to protect our planet for future generations. It challenges us to consider our impact on the environment and to seek innovative solutions to the pressing issues of climate change and resource depletion. Ultimately, the Sun is more than just a star in the sky. It is a source of life, energy, and inspiration. Its presence shapes our planet and our lives in countless ways, influencing everything from weather patterns to the rhythms of life. As we continue to study and understand the Sun, we are drawn into a larger narrative about the universe and our place within it. In contemplating the future of the Sun, we must also consider the legacy we wish to leave behind. The choices we make today regarding energy consumption, environmental stewardship, and technological innovation will shape the world for generations to come. By harnessing the Sun's energy responsibly and sustainably, we can create a future that honors the incredible power of this celestial body while protecting the planet that is our home. The Sun stands as a testament to the beauty and complexity of the universe. It is a constant reminder of the delicate balance between energy, life, and the environment. As we gaze upon the Sun, we are reminded of our connection to the cosmos and the responsibilities we hold as caretakers of our planet. The exploration of the Sun will continue to yield discoveries that enrich our understanding of the universe and inspire future generations to reach for the stars. In conclusion, the Sun is not just a distant celestial object. It is the heart of our solar system, a source of energy, and a driving force in the evolution of life on Earth. As we unravel the mysteries of the Sun, We gain insights not only into the workings of our star but also into the fundamental processes that govern the universe. The sun's influence permeates every aspect of our lives, shaping our environment, fueling our technology, and inspiring our imagination. As we look to the future, the lessons learned from studying the sun will guide our efforts to create a sustainable and vibrant world, one that honors the extraordinary energy that sustains us all. The sun's importance extends to our understanding of the greater universe. By studying the sun, scientists are able to draw parallels with other stars in our galaxy, allowing us to grasp fundamental concepts of stellar evolution, fusion, and cosmic dynamics. The sun, classified as a G-type main sequence star, or yellow dwarf, provides a reference point for astronomers studying stars of various types, from massive blue giants to dim red dwarfs. Its life cycle is a template for understanding how stars are born, live, and die, giving us a glimpse into the fate of many other stars scattered throughout the universe. Our sun is currently in a stable phase of its life, known as the main sequence, where it has been for about 4.6 billion years. During this phase, the sun burns hydrogen in its core, converting it into helium through nuclear fusion. This process generates immense amounts of energy, which radiates outwards and provides the light and heat that sustain life on Earth. The sun's ability to maintain this steady output of energy over billions of years is what makes life on Earth possible, as it provides the stability needed for ecosystems to develop and thrive. However, like all stars, the sun's time in the main sequence is finite. It is expected to remain in this stable phase for about another 5 billion years before it begins to run out of hydrogen fuel in its core. When this happens, the sun will undergo dramatic changes, marking the beginning of the end of its life cycle. As the hydrogen supply dwindles, the core will contract, and the outer layers of the sun will expand, turning the sun into a red giant. In this phase, the sun will become much larger and cooler on its surface, eventually engulfing the inner planets of the solar system, including Mercury and Venus, and possibly Earth. Though this transformation is billions of years away, it serves as a stark reminder of the impermanence of all things in the universe. As the sun transitions into a red giant, the conditions that currently sustain life on Earth will no longer exist. The oceans will evaporate, the atmosphere will be stripped away, and any remaining life will perish as temperatures soar beyond survivable levels. However, before this catastrophic phase begins, humanity may already have explored and colonized other worlds, leaving Earth behind in search of new homes. Once the sun has exhausted its fuel and shed its outer layers, it will leave behind a core that will become a white dwarf, a dense, hot remnant of its former self. The white dwarf will slowly cool over billions of years, gradually fading away into a cold, dark object known as a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. In its final stages, the sun will no longer emit light or heat, marking the end of its stellar life. This fate, while seemingly far removed from our current experience, underscores the inevitability of cosmic cycles and the transitory nature of all celestial bodies. The future of the sun also has implications for the broader understanding of planetary systems and how they evolve. As the sun transforms, the gravitational dynamics of the solar system will change, potentially causing disruptions in the orbits of planets and other celestial bodies. The outer planets, like Jupiter and Saturn, will likely remain unaffected by the sun's expansion, but their moons and any potential habitability they may have will be influenced by the changing solar environment. The study of these future changes informs our understanding of how planetary systems around other stars may evolve over time, helping scientists predict the habitability of exoplanets orbiting distant stars. The concept of solar evolution is not just a theoretical exercise. It has real implications for the future of space exploration and human survival. As we look to the stars for potential new homes, understanding the life cycles of stars becomes crucial in identifying habitable worlds. Just as the sun provides the necessary conditions for life on Earth, so too will the stars of distant solar systems play a role in determining whether other planets could sustain life. The study of stellar evolution and planetary habitability is a central focus of modern astrophysics and astrobiology, as it offers insight into the potential for life beyond Earth. While the eventual demise of the sun may seem daunting, it also provides an opportunity for humanity to expand its horizons. As our understanding of the universe deepens, so too does our potential to explore and inhabit other worlds. The search for exoplanets, planets orbiting stars outside our solar system, has already yielded thousands of discoveries, some of which lie within the habitable zones of their stars, where conditions might support liquid water and, by extension, life. As we study the Sun and other stars, we learn not only about their life cycles but also about the potential for other civilizations to exist in the cosmos. The Drake equation, a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, hinges on our understanding of stars and planetary systems. By studying our Sun and its planets, we gain insights into the factors that might allow life to arise elsewhere, fueling the ongoing search for signs of extraterrestrial intelligence. The search for life beyond Earth and the exploration of distant stars are part of a broader quest to understand our place in the universe. The Sun, as our closest star, serves as a gateway to this cosmic exploration. It teaches us about the forces that shape the cosmos, the delicate balance that sustains life, and the vastness of time and space. As we continue to study the Sun, we are reminded of both our fragility and our potential to reach beyond the confines of our planet and explore the mysteries of the universe. In this context, the study of the Sun is not just an academic pursuit, it is a journey of discovery that touches on some of the most profound questions humans have ever asked. What is the nature of the universe? Are we alone in the cosmos? How can we harness the power of the Sun to ensure the survival of our species? These questions, while rooted in science, also evoke a sense of wonder and curiosity that has driven human exploration for millennia. In the same way that ancient civilizations looked to the Sun for guidance and inspiration, we too find ourselves drawn to its light as we seek to understand the cosmos. The Sun is a constant reminder of the beauty and mystery of the universe, a celestial body that both sustains us and challenges us to explore beyond the known. The Sun's role in the development of life on Earth, its influence on our climate and energy systems, and its place in the broader cosmic story make it one of the most fascinating objects of study in science. Its behavior, both predictable and volatile, offers endless opportunities for discovery and innovation. From the intricate dance of its magnetic fields to the vast reaches of its heliosphere, the Sun continues to captivate scientists and laypeople alike, serving as both a source of knowledge and a symbol of humanity's enduring quest for understanding. As we continue to unlock the secrets of the Sun, we do so with the knowledge that our star is just one of billions in the universe, each with its own story to tell. The exploration of the Sun is, in many ways, the beginning of a much larger journey, one that will take us beyond the solar system and into the farthest reaches of the cosmos. The lessons we learn from the Sun will guide us as we embark on this journey, helping us to navigate the complexities of space and time. The Sun is more than just a star, it is a symbol of life, energy, and the infinite possibilities of the universe. It reminds us of the interconnectedness of all things, from the smallest particles to the largest galaxies. As we gaze upon the Sun, we are reminded of our place in the cosmos and the incredible journey that lies ahead. The Sun, in all its brilliance, will continue to light our way as we explore the mysteries of the universe and seek to understand the wonders of existence. The Sun's significance in the broader context of our galaxy and the universe cannot be overstated. As we study its behavior and structure, we gain insights into fundamental astrophysical processes that govern not only our solar system but also countless other star systems scattered across the cosmos. The Sun's relative proximity allows us to observe phenomena that would otherwise remain hidden in the depths of space, offering a unique window into the workings of the universe at large. One of the Sun's most remarkable features is its magnetic field, which extends far beyond the surface into the solar corona and the surrounding space. This magnetic field is responsible for many of the Sun's more dramatic activities, such as sunspots, solar flares, and coronal mass ejections, CMEs. These phenomena, while visually captivating, have far-reaching effects on the space environment and, by extension, Earth itself. The Sun's magnetic field is generated by the movement of electrically charged particles within its convective zone. This movement creates a complex and ever-changing magnetic field, which twists and loops in ways that are still not fully understood. The most visible manifestation of this magnetic activity is the appearance of sunspots, dark regions on the sun's surface where the magnetic field is particularly strong. Sunspots are cooler than the surrounding areas, which is why they appear dark, but they are also indicative of intense magnetic activity beneath the surface. Sunspots often serve as the origin points for solar flares and CMEs. Solar flares are sudden and powerful bursts of radiation that can disrupt communications and navigation systems on Earth, while CMEs are massive eruptions of solar material that can cause geomagnetic storms when they collide with Earth's magnetosphere. These storms can interfere with satellite operations, power grids, and even radio communications, making solar weather a critical area of study for scientists and engineers. The study of solar weather, also known as space weather, has become increasingly important in our technologically dependent world. As we rely more on satellites for communication, navigation, and data transmission, the need to understand and predict solar activity becomes more urgent. A particularly strong solar flare or CME could cause widespread disruptions to global infrastructure, affecting everything from air travel to electricity distribution. This has led to the development of solar observatories and space weather prediction models designed to monitor and forecast solar activity. The sun's magnetic field also plays a crucial role in shaping the heliosphere, a vast bubble of solar wind that envelopes the entire solar system. The heliosphere acts as a protective shield, deflecting cosmic rays and interstellar particles that would otherwise bombard Earth and the other planets. The boundary of the heliosphere, known as the heliopause, marks the edge of the sun's influence and the beginning of interstellar space. Understanding the dynamics of the heliosphere is important not only for protecting spacecraft and astronauts from cosmic radiation but also for understanding how stars interact with their surrounding environments. The solar wind, a continuous stream of charged particles emitted by the sun, is another key aspect of solar activity. The solar wind carries the sun's magnetic field out into space, shaping the environment of the entire solar system. When the solar wind interacts with Earth's magnetosphere, it creates beautiful auroras near the poles, but it can also disrupt communication systems and pose a hazard to satellites and astronauts. By studying the solar wind, scientists hope to better understand how the sun's activity affects space weather and develop strategies to mitigate its impact on modern technology. The sun's influence extends even further through the phenomenon known as the solar cycle, an approximately 11-year cycle of increasing and decreasing solar activity. During the solar maximum, the sun is more active, with more sunspots, flares, and CMEs, while during the solar minimum, activity decreases. The solar cycle has been observed for centuries and is thought to be linked to changes in the sun's magnetic field. Understanding the solar cycle helps scientists predict periods of increased solar activity and prepare for potential disruptions to technology and infrastructure on Earth. The sun continues to inspire awe and wonder. Its daily journey across the sky, the warmth it provides, and the vibrant colors it paints at dawn and dusk remind us of our connection to the natural world. The sun's light is essential to our existence, and without it, life as we know it would cease to exist. As we gaze at the sun, whether in admiration or scientific study, we are reminded of the intricate web of life that depends on its energy. The sun is also a symbol of power and innovation. For centuries, humans have sought to harness its energy, from ancient sun-dried crops to modern solar panels. Solar energy is one of the most promising sources of renewable energy, offering a clean and abundant alternative to fossil fuels. Advances in solar technology are bringing us closer to a future where the sun's energy can power entire cities, reduce our dependence on non-renewable resources, and mitigate the impacts of climate change. Solar panels, photovoltaic cells, and concentrated solar power systems are just a few of the ways we are learning to capture and use the sun's energy more efficiently. Solar energy is already playing a significant role in reducing greenhouse gas emissions and providing electricity to remote and underserved areas. As technology continues to improve, the potential for solar energy to transform our energy systems grows, making it a key player in the transition to a more sustainable and resilient energy future. The sun, which has sustained life on Earth for billions of years, may also hold the key to solving some of the most pressing environmental challenges of our time. The sun's energy also powers photosynthesis, the process by which plants convert sunlight into chemical energy. This process forms the foundation of nearly all life on Earth, as plants serve as the primary producers in most ecosystems. Photosynthesis not only provides the food and oxygen necessary for life but also plays a crucial role in regulating the Earth's atmosphere by absorbing carbon dioxide. The sun's role in driving photosynthesis highlights its essential place in the Earth's biological systems and underscores the interconnectedness of life on our planet. As we look to the future, the sun's role in supporting life and driving technological advancement will continue to grow. Solar energy has the potential to revolutionize industries, from agriculture to space exploration. Solar-powered drones, spacecraft, and vehicles are already being developed, paving the way for a future where solar energy plays a central role in powering human activities both on Earth and beyond. The sun, which has guided explorers and innovators for centuries, remains a beacon of inspiration for those seeking to push the boundaries of human achievement. The exploration of the sun itself is another exciting frontier in space science. NASA's Parker Solar Probe, launched in 2018, is the first mission to touch the sun, venturing closer to its surface than any spacecraft before it. The probe's mission is to study the outer corona, the solar wind, and the sun's magnetic fields in unprecedented detail, providing insights into the fundamental processes that drive solar activity. This mission represents a major leap forward in our understanding of the sun and its impact on the solar system. The Parker Solar Probe is expected to answer many long-standing questions about the sun, such as how the corona can be hotter than the sun's surface, why the solar wind accelerates as it moves away from the sun, and what mechanisms drive solar flares and CMEs. These discoveries will not only deepen our understanding of the sun but also enhance our ability to predict space weather and protect Earth-based technologies from solar storms. As we continue to study the sun, both through ground-based observatories and space missions, we are reminded of the sun's profound influence on all aspects of life. Its light and heat sustain us, its magnetic activity shapes our environment, and its energy offers solutions to some of the most pressing challenges we face. The sun is both a familiar presence in our daily lives and a complex and dynamic star that holds countless mysteries waiting to be unraveled. In many ways, the sun serves as a reminder of our connection to the cosmos. Though we are bound to Earth, the sun's light and energy reach across the solar system and beyond, linking us to the vast expanse of space. The study of the sun, like all astronomical research, is a way of exploring our place in the universe and seeking to understand the forces that shape our world and beyond. As our understanding of the sun continues to evolve, we are also increasingly aware of its relationship with Earth's climate system. The sun is the primary driver of Earth's climate, and variations in solar output can influence weather patterns, temperature fluctuations, and even long-term climate changes. Over geological timescales, the sun has gone through cycles of variability, affecting the Earth's climate in profound ways. Research indicates that changes in solar radiance, the amount of sunlight reaching the Earth, can correlate with climatic events. For instance, periods of increased solar activity, known as solar maxima, can coincide with warmer temperatures, while solar minima, such as the Maunder minimum during the 17th century, are associated with cooler conditions. Understanding these relationships is essential not only for historical climate reconstructions but also for predicting future climate trends in a warming world. In addition to direct effects, the sun also influences the Earth's climate through its interactions with the atmosphere. Solar radiation drives atmospheric circulation patterns, which in turn affect weather systems. For example, increased solar activity can lead to changes in the jet streams, altering weather patterns across continents. This interconnection between solar activity and atmospheric dynamics highlights the complexity of the Earth's climate system and underscores the importance of studying the sun in the context of climate science. Moreover, the sun's role in climate dynamics is complicated by the presence of greenhouse gases in the atmosphere. While increased solar radiation can lead to warming, human activities have significantly altered the balance of greenhouse gases, creating additional layers of complexity in understanding climate change. This has led to ongoing research aimed at disentangling the contributions of solar variability from anthropogenic factors, as scientists strive to build accurate climate models. One particularly intriguing area of research involves the role of the sun in natural climate variability, such as the El Niño and La Niña phenomena. These oscillations in ocean temperatures can have significant effects on global weather patterns, and some studies suggest that variations in solar activity may influence the timing and intensity of these events. Understanding these connections is crucial for improving climate predictions and preparing for the impacts of climate variability on ecosystems and human societies. As we explore the sun's past, we also look toward its future. The sun is approximately 4.6 billion years old and is expected to undergo significant changes over the next several billion years. Currently, the sun is in the stable phase of its life cycle known as the main sequence, where it fuses hydrogen into helium in its core. However, as it exhausts its hydrogen supply, the sun will enter the next phase of its life cycle, eventually becoming a red giant. During the red giant phase, the sun will expand significantly, potentially engulfing the inner planets, including Earth. This transformation will alter the solar system in dramatic ways, changing the environment of the remaining planets and potentially stripping away their atmospheres. Understanding the processes leading to this eventual fate is not only essential for solar physics, but also raises questions about the long-term habitability of Earth and the future of life in the solar system. Ultimately, the study of the sun and its future serves as a reminder of the transient nature of celestial bodies and the impermanence of our own existence. As we seek to understand the life cycles of stars, we also confront our place in the universe and the limitations of human life against the vastness of cosmic time. This realization encourages a greater appreciation for our home planet and the delicate balance that sustains life. In contemplating the sun's eventual demise, we also turn our gaze to the possibility of life beyond Earth. The sun has provided the necessary conditions for life to thrive on our planet, but what happens to the solar system as it approaches the end of the sun's life cycle? The search for extraterrestrial life is an ever-expanding field of inquiry, and understanding how solar systems evolve can provide insights into the potential for life elsewhere in the universe. As we explore distant exoplanets, researchers consider factors such as the host star's type, size, and stability in determining whether a planet may be capable of supporting life. The study of solar systems beyond our own has revealed a staggering diversity of planetary environments, from gas giants orbiting close to their stars to Earth-like planets situated in the habitable zone. These discoveries prompt exciting questions. How do these planets evolve? What are the conditions necessary for life to emerge? And could we one day inhabit such worlds beyond our solar system? The ongoing advancements in space exploration and telescope technology are providing us with unprecedented opportunities to investigate these questions. Missions such as the Kepler Space Telescope and the Transiting Exoplanets Survey Satellite, TESS, have identified thousands of exoplanets, many of which reside in the habitable zones of their stars, where conditions might be right for liquid water to exist, a key ingredient for life as we know it. Additionally, the James Webb Space Telescope, JWST, with its advanced infrared capabilities, is poised to analyze the atmospheres of these distant worlds, searching for signs of habitability or even direct evidence of biological activity. The study of exoplanets is not just an academic pursuit, it has practical implications for our understanding of the Earth and its climate. By examining the atmospheres of other planets, scientists can develop models to better predict how our own climate may change in response to various factors, including solar activity. The lessons learned from the sun can inform our understanding of planetary systems, particularly in the context of habitability and climate dynamics. As we investigate the potential for life beyond Earth, we must also confront philosophical questions about our place in the universe. The realization that life could exist elsewhere challenges our understanding of what it means to be human and raises profound questions about intelligence, consciousness, and the future of our species. If we discover life on another planet, what would it mean for humanity? Would it lead to a greater understanding of our own existence, or could it spark competition and conflict? These questions underscore the importance of responsible exploration and the need for ethical frameworks as we advance our capabilities in space exploration. In addition to the search for extraterrestrial life, the sun remains central to discussions about the future of human civilization. The increasing reliance on technology and the impact of climate change pose significant challenges for humanity in the coming decades. The sun's energy presents a viable solution to some of these challenges, particularly as we transition to renewable energy sources. Solar technology is rapidly advancing, with new innovations in efficiency, storage, and integration into the energy grid. Solar power is becoming more accessible and affordable, making it a key player in global efforts to reduce carbon emissions and combat climate change. Countries around the world are investing in solar infrastructure, from large-scale solar farms to residential rooftop installations. These developments are not only contributing to energy independence but also creating jobs and stimulating local economies. As the demand for clean energy grows, the role of the sun in powering our future becomes increasingly vital. Moreover, the sun's role in driving photosynthesis and supporting ecosystems is critical in the context of sustainable agriculture. As the global population continues to grow, ensuring food security while minimizing environmental impacts is a pressing challenge. Innovations in agricultural practices, such as vertical farming and precision agriculture, can enhance food production efficiency while reducing the ecological footprint. The sun's energy remains a foundational element in these efforts, supporting plant growth and sustainable farming practices. The sun's influence also extends into the realm of human health and well-being. Sunlight plays a crucial role in regulating circadian rhythms, influencing sleep patterns, and supporting mental health. Exposure to natural light has been linked to improved mood, increased productivity, and enhanced overall well-being. Understanding the relationship between sunlight, health, and lifestyle is essential as we navigate the challenges of modern living, particularly in urban environments where access to natural light may be limited. As we consider the myriad ways the sun impacts our lives, it becomes clear that it is not just a distant star but a vital partner in the story of life on Earth. The sun's energy supports ecosystems, drives weather patterns, and shapes human societies. Our understanding of the sun and its influence is continually evolving, and ongoing research is critical for addressing the challenges of the future. In the broader cosmic context, the sun is also a reminder of the interconnectedness of all things. As a star, it is part of a larger stellar community within the Milky Way galaxy. Our galaxy contains billions of stars, each with its own set of planets, moons, and potential for life. The formation and evolution of stars are interconnected processes that shape the very fabric of the universe. Studying the sun helps us understand not only its behavior but also the life cycles of stars and their role in the cosmic ecosystem. Moreover, the sun is a stellar archetype, allowing astronomers to study the characteristics of stars across the universe. By examining the sun's structure, composition, and behavior, scientists can make inferences about other stars and their potential for hosting planets. This comparative analysis deepens our understanding of stellar evolution, including the processes that lead to the formation of planets and the conditions necessary for life. The story of the sun is intertwined with the history of human civilization. From ancient cultures that worship the sun as a deity to modern scientists unlocking its secrets, our relationship with this celestial body has shaped our understanding of the universe and our place within it. As we continue to explore the mysteries of the sun, we are not only gaining knowledge about our solar system but also forging connections with the broader cosmos. In the face of an ever-changing universe, the sun remains a constant presence, a source of light, energy, and inspiration. As we look to the future, our relationship with the sun will only deepen. The lessons we learn from studying our nearest star will inform our approach to challenges on Earth and beyond, guiding us as we navigate the complexities of a rapidly evolving world. Ultimately, the sun embodies the interconnectedness of life, energy, and existence. It is a reminder that we are part of a larger cosmic tapestry, bound by the forces of nature and the laws of physics. As we embrace this understanding, we can cultivate a deeper appreciation for the sun's gifts and its critical role in the story of life on Earth. Through exploration, innovation, and responsible stewardship, we can harness the power of the sun to build a sustainable and thriving future for generations to come. The sun is more than just a star. It is a vital source of life, energy, and inspiration. Its complex dynamics and profound influence extend beyond the solar system, shaping the universe and the life it nurtures. As we continue to explore the mysteries of the sun, we deepen our understanding of ourselves and the cosmic forces that govern our existence. The journey of discovery is ongoing, and the sun will forever hold a special place in the hearts and minds of those who seek to understand the universe and our place within it. As we delve deeper into the implications of our relationship with the sun, we must also acknowledge the vital role of education and public awareness in fostering a greater understanding of solar science. Increasingly, efforts are being made to communicate the importance of solar research and the implications of solar activity for our daily lives. This outreach is crucial not only for inspiring the next generation of scientists but also for informing the general public about the intricate connections between solar dynamics, climate change, and technological advancements. Educational programs aimed at explaining the sun's processes and its impact on Earth can stimulate interest in science and promote critical thinking. Initiatives in schools, community centers, and online platforms can engage individuals of all ages in discussions about astronomy, energy, and the environment. By making solar science accessible and engaging, we empower people to understand and appreciate the complexities of the universe while fostering a culture of curiosity and exploration. Moreover, the development of citizen science projects enables the public to participate actively in solar observations and research. These initiatives not only enhance our understanding of solar phenomena but also cultivate a sense of community and shared purpose. By involving individuals in real scientific endeavors, we can bridge the gap between scientific research and everyday life, reinforcing the notion that everyone has a role to play in advancing knowledge and promoting sustainability. As we explore the sun's influence on Earth, we must also consider the implications of space weather. Solar flares, coronal mass ejections, and other solar events can have far-reaching effects on our planet's magnetosphere, potentially disrupting communication systems, satellites, and power grids. Understanding the dynamics of these events and developing predictive models is essential for mitigating their impacts. The ongoing collaboration between scientists, engineers, and policymakers is crucial to safeguarding our technology-dependent society from the potential hazards posed by space weather. Research into the sun's magnetic field is particularly critical in this context. The sun's magnetic field is dynamic and can undergo significant changes, leading to solar storms that may threaten our technological infrastructure. By studying solar magnetic fields and their interactions with the solar wind, scientists are working to develop accurate forecasting systems that can provide early warnings of impending space weather events. These systems will not only protect satellites and communication networks but also help ensure the safety of astronauts during missions beyond low Earth orbit. In light of these challenges, international cooperation in solar research and monitoring has become increasingly important. Collaborative efforts among space agencies, universities, and research institutions facilitate the sharing of data, resources, and expertise. Initiatives such as the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe are prime examples of global collaboration aimed at advancing our understanding of the Sun. These missions not only deepen our knowledge of solar dynamics, but also foster a sense of unity among nations in the pursuit of scientific discovery. The implications of solar research extend beyond Earth and can inform our understanding of other star systems and the broader cosmos. By studying the Sun's behavior, we can gain insights into the life cycles of other stars, the formation of planetary systems, and the conditions necessary for life to emerge. The knowledge we acquire about our star has the potential to reshape our understanding of stellar evolution and inform the search for habitable exoplanets. As we consider the future of humanity in the context of the Sun, we must also contemplate the ethical implications of our relationship with this powerful celestial body. The energy harnessed from the Sun offers incredible potential for sustainable development and a more equitable distribution of resources. However, the transition to solar energy must be approached thoughtfully and responsibly, taking into account the social, economic, and environmental impacts of new technologies. The shift towards solar energy requires a multifaceted approach that prioritizes equity and inclusivity. It is essential to engage marginalized communities and ensure that they have access to the benefits of solar technology. This involves not only providing affordable solar solutions but also creating job opportunities in the renewable energy sector and promoting education in solar technology. By addressing systemic inequalities, we can build a more sustainable and just future. Furthermore, as we embrace solar energy, we must also consider the implications for wildlife and natural ecosystems. Large-scale solar farms can have significant effects on land use, habitat loss, and biodiversity. To minimize these impacts, careful planning and consideration of ecological factors are essential. Innovative designs, such as agrivoltaics, integrating solar panels with agricultural practices, can provide solutions that benefit both energy production and biodiversity. Artistic expressions inspired by the sun can also serve as powerful vehicles for advocacy and awareness. Artists, musicians, and writers have the ability to convey complex scientific concepts and raise awareness about the importance of protecting our environment. By intertwining science and art, we can engage audiences on multiple levels, fostering a deeper appreciation for the sun and its vital role in sustaining life on Earth. In addition to artistic endeavors, the role of literature in exploring our relationship with the sun and the broader universe cannot be overlooked. Science fiction has long provided a platform for imagining the future, challenging our understanding of humanity's place in the cosmos. Authors like Arthur C. Clarke and Isaac Asimov have inspired generations to contemplate the possibilities of space exploration and the potential for life beyond Earth. These narratives provoke thought and stimulate curiosity, encouraging readers to envision a future where humanity continues to explore the mysteries of the universe. As we navigate the challenges of the present and look toward the future, our relationship with the sun will undoubtedly evolve. The ongoing advancements in solar research, energy technology, and space exploration will continue to shape our understanding of this vital celestial body and its role in the universe. By fostering a culture of curiosity, collaboration, and responsible stewardship, we can harness the sun's power to build a sustainable and thriving future for all. In summary, the sun is not merely a source of light and heat. It is a complex and dynamic star that influences every aspect of life on Earth and beyond. Our understanding of the sun's processes, its impact on climate and weather, and its potential for sustainable energy solutions is continually expanding. As we confront the challenges of the future, the sun will remain a guiding force, inspiring curiosity, innovation, and collaboration in our quest to understand the cosmos and our place within it. The intricate relationship between humanity and the sun reminds us of the interconnectedness of all things, urging us to cultivate a deeper appreciation for the natural world and the cosmos at large. As we strive to explore, understand, and responsibly utilize the sun's energy, we not only enhance our quality of life but also honor the delicate balance that sustains existence on our planet. The journey of discovery is ongoing, and the sun will continue to illuminate our path as we seek answers to the profound questions of life, energy, and the universe itself. As our exploration of the sun continues, it is important to recognize the multifaceted nature of our relationship with this central star. The sun serves as a key player in our understanding of fundamental scientific principles, and its study transcends disciplines ranging from astrophysics to environmental science, engineering, and even philosophy. Each field brings unique perspectives and methodologies that contribute to a holistic understanding of solar phenomena and their implications for life on Earth. Astrophysics, in particular, focuses on understanding the sun as a star, a massive ball of plasma undergoing nuclear fusion. This discipline examines the processes that drive the sun's energy production and the dynamics of its magnetic field, which plays a crucial role in solar activity. Research into solar flares, coronal mass ejections, and sunspots enhances our understanding of stellar behavior and the underlying physical laws governing these phenomena. The study of the sun also intersects with environmental science, as researchers investigate the connections between solar activity and Earth's climate. Historical records reveal that variations in solar output can influence climate patterns, such as the Little Ice Age, which was characterized by colder temperatures in Europe and North America during the 17th century. Understanding these interactions is crucial for climate modeling and predicting future climate scenarios. By examining the sun's influence on Earth's climate system, scientists can develop more accurate models to inform policy decisions aimed at addressing climate change. Moreover, engineering plays a pivotal role in harnessing solar energy for practical applications. Innovations in solar panel technology have led to increased efficiency and reduced costs, making solar energy a viable alternative to fossil fuels. Research into energy storage systems, such as batteries and thermal storage, is critical for maximizing the utility of solar power, particularly in regions with variable sunlight. Engineers and scientists are collaborating to develop integrated solutions that can support energy independence and sustainability in an increasingly electrified world. The philosophical implications of our relationship with the sun are equally profound. As we grapple with the existential questions of life, purpose, and our place in the universe, the sun serves as a focal point for contemplation. The vastness of the cosmos, illuminated by the light of countless stars, invites us to ponder the nature of existence and the possibility of life beyond our planet. The sun, as our nearest star, becomes a metaphor for exploration and discovery, representing the quest for knowledge that has defined humanity for centuries. As we venture further into the cosmos, our understanding of the sun's role in the universe will continue to evolve. Future space missions, such as those planned by NASA and other space agencies, aim to enhance our knowledge of solar dynamics and their implications for both our solar system and the broader galactic environment. The Solar Orbiter mission, launched in 2020, seeks to study the sun's poles and its magnetic field, providing insights into the solar cycle and the mechanisms behind solar activity. Such missions will undoubtedly yield new discoveries that deepen our understanding of the sun and its connections to other celestial bodies. In addition to exploration, technological advancements in data analysis and modeling techniques are transforming our approach to solar research. Machine learning and artificial intelligence are being applied to analyze vast datasets generated by solar observatories, enabling scientists to identify patterns and make predictions about solar behavior with unprecedented accuracy. This integration of technology and science opens new avenues for understanding the complexities of the sun and its impact on our planet. Public engagement and participation in solar research are also essential for fostering a culture of curiosity and scientific literacy. Initiatives that encourage citizen science and community involvement in solar observations help demystify scientific research and promote a sense of ownership in the pursuit of knowledge. Engaging the public through educational programs, workshops, and outreach events empowers individuals to contribute to our understanding of the sun while cultivating a greater appreciation for the wonders of the universe. As we reflect on the significance of the sun in our lives, it is vital to acknowledge the environmental challenges facing our planet. Climate change, habitat destruction, and biodiversity loss pose existential threats to ecosystems and human societies alike. The sun's energy, while a powerful tool for sustainable development, must be harnessed thoughtfully and responsibly. We must consider the ecological impacts of solar infrastructure and strive to implement solutions that prioritize environmental integrity and social equity. The transition to a sustainable future requires a collective effort that transcends borders and disciplines. Individuals must work collaboratively to develop and implement policies that promote renewable energy, protect ecosystems, and address the social dimensions of climate change. By embracing a holistic approach that integrates science, technology, policy, and community engagement, we can create a more resilient and equitable society in harmony with the sun and the natural world. In this context, the sun emerges not only as a source of energy, but also as a symbol of hope and renewal. Its consistent rise and set serve as a reminder of the cyclical nature of life and the potential for regeneration. Just as the sun brings light to each new day, our collective efforts towards sustainability can illuminate pathways to a brighter, more sustainable future for generations to come. The ongoing exploration of the sun also serves as a humbling reminder of the vastness of the universe and our place within it. The more we learn about our star, the more we realize how little we truly know about the cosmos. Each discovery sparks new questions, urging us to continue our pursuit of knowledge and understanding. The journey of exploration is never-ending, and the quest to unravel the mysteries of the sun will inspire future generations of scientists, thinkers, and dreamers. As we stand on the precipice of a new era in solar research and exploration, we must embrace the challenges and opportunities that lie ahead. The sun, with its radiant energy and complex dynamics, invites us to look beyond our immediate concerns and consider the broader implications of our actions. By cultivating a deeper understanding of the sun and its interconnectedness with all life, we can foster a sense of stewardship for our planet and the cosmos. In conclusion, the sun is a central figure in our understanding of the universe and our place within it. Its profound influence shapes our lives, drives our technological advancements, and inspires our quest for knowledge. As we navigate the complexities of the future, we must remain committed to responsible exploration, sustainable practices, and a collaborative approach to addressing the challenges we face. The sun, in all its brilliance, will continue to guide us on this journey, illuminating the path toward a sustainable and equitable future for all. The relationship between humanity and the sun is one of mutual dependence and inspiration, urging us to explore, understand, and cherish the natural world. By embracing this connection, we can harness the power of the sun to illuminate not only our physical environment but also our collective journey toward a better future. With the advent of scientific inquiry during the Renaissance, humanity's understanding of the sun began to shift dramatically. The heliocentric model proposed by Copernicus, which placed the sun at the center of the solar system, challenged the long-held geocentric view that had dominated for centuries. This revolutionary idea laid the groundwork for modern astronomy and significantly altered humanity's perception of its place in the universe. Figures like Galileo and Kepler further advanced our understanding of celestial mechanics, allowing for more accurate predictions of planetary movements and paving the way for future discoveries. The development of telescopes in the 17th century marked a pivotal moment in solar observation. Galileo's observations of sunspots and the phases of Venus provided critical evidence supporting the heliocentric model. This shift in perspective not only expanded our knowledge of the sun but also ignited a fascination with the cosmos that continues to this day. The subsequent centuries witnessed the rise of astronomy as a scientific discipline, leading to advancements in our understanding of stellar processes, solar phenomena, and the fundamental laws governing the universe. As we transitioned into the modern era, the technological innovations of the 20th and 21st centuries revolutionized solar research. Spacecraft such as the Solar Dynamics Observatory, SDO, and the Parker Solar Probe have provided unprecedented insights into the sun's atmosphere, magnetic field, and solar wind. These missions have enabled scientists to capture high-resolution images of solar activity, revealing intricate details about solar flares, coronal mass ejections, and the structure of the solar corona. Moreover, advancements in instrumentation and data analysis have enhanced our ability to monitor solar activity in real time. The integration of satellite-based observations with ground-based telescopes has created a comprehensive framework for studying the sun and its effects on Earth. This wealth of data not only informs our understanding of solar processes, but also plays a crucial role in predicting space weather events that can impact technology and human activities. One of the most significant discoveries in solar research has been the identification of the solar cycle, an approximately 11-year cycle during which solar activity fluctuates between periods of high and low activity. This cycle is characterized by the appearance and disappearance of sunspots, which are areas of intense magnetic activity on the sun's surface. Understanding the solar cycle is essential for predicting space weather and its potential impacts on Earth's magnetosphere and technological systems. As we deepen our understanding of the sun, we must also consider its relationship with other celestial bodies in the solar system. The sun's gravitational influence governs the orbits of planets, asteroids, and comets, creating a delicate balance within the solar system. The interactions between solar wind and planetary atmospheres can shape the conditions for life, as evidenced by the contrasting climates of Venus, Earth, and Mars. Studying these relationships can provide valuable insights into the potential for life on other planets and the factors that contribute to habitability. The exploration of our solar system, particularly missions to Mars and the outer planets, has reignited interest in the role of the Sun in shaping planetary environments. The findings from these missions contribute to our understanding of planetary atmospheres, geological processes, and the potential for life beyond Earth. By examining the similarities and differences between our planet and its neighbors, we can gain a clearer picture of the conditions necessary for life to thrive and the importance of the Sun in supporting those conditions. Additionally, the Sun serves as a vital reference point for understanding other stars throughout the universe. As the most studied star, the Sun provides a benchmark for astrophysicists to compare and contrast with other stellar bodies. Insights gained from solar research inform our understanding of stellar evolution, the life cycles of stars, and the mechanisms that drive nuclear fusion. The knowledge gained from studying the Sun extends beyond our solar system, enhancing our comprehension of the diverse array of stars scattered across the cosmos. The ongoing quest for knowledge about the Sun also raises important questions about the future of humanity. As we look to the stars and contemplate the possibility of interstellar travel, our understanding of the Sun will play a critical role in shaping our aspirations and technological advancements. The challenges of traveling to other star systems require innovations in energy generation, propulsion technologies, and life support systems, all of which are influenced by our knowledge of solar dynamics and energy harnessing. Furthermore, as we confront the pressing issues of climate change and resource depletion, the Sun presents an opportunity for sustainable development through solar energy. Transitioning to renewable energy sources, particularly solar power, can mitigate the impacts of fossil fuel consumption and reduce greenhouse gas emissions. By investing in solar infrastructure and technologies, we can harness the Sun's energy to power our homes, businesses, and communities, fostering a more sustainable future for generations to come. The transition to a solar-powered society, however, is not without its challenges. It requires a comprehensive approach that considers technological advancements, policy frameworks, and social dynamics. Governments, businesses, and individuals must collaborate to create an enabling environment for solar energy adoption, ensuring that marginalized communities are not left behind in the transition. Education and awareness campaigns play a crucial role in informing the public about the benefits of solar energy and fostering a culture of sustainability. In addition to harnessing solar energy for electricity generation, innovative solutions such as solar thermal energy, which captures the Sun's heat for various applications, can contribute to reducing our reliance on fossil fuels. Solar thermal systems can be employed for heating water, powering industrial processes, and even providing cooling solutions. These diverse applications highlight the versatility of solar energy and its potential to transform various sectors of the economy. As we embrace the power of the Sun, we must also remain vigilant about the environmental impacts of solar energy production. The manufacturing processes for solar panels, while increasingly efficient, still pose challenges related to resource extraction, waste management, and ecosystem disruption. Developing sustainable practices within the solar industry is paramount to ensuring that our pursuit of renewable energy aligns with our broader environmental goals. In this context, the principles of circular economy and sustainable design come into play. By prioritizing the reuse, recycling, and repurposing of materials used in solar technology, we can minimize waste and reduce the environmental footprint of solar energy production. Innovations in materials science and engineering are essential for creating solar technologies that are not only efficient but also environmentally friendly. Moreover, the integration of solar energy into urban planning and infrastructure development can foster resilience and sustainability. Designing cities with solar energy in mind can enhance energy efficiency, reduce carbon emissions, and promote a higher quality of life for residents. Urban environments can benefit from solar panels installed on rooftops, solar canopies in public spaces, and innovative designs that optimize sunlight exposure. By incorporating solar energy solutions into urban planning, we can create vibrant and sustainable communities that thrive in harmony with the Sun. As we contemplate the future of solar energy, it is essential to recognize the role of policy and governance in shaping the transition to a sustainable energy landscape. Governments play a critical role in establishing supportive regulatory frameworks, providing incentives for solar adoption, and investing in research and development. Collaborative efforts among nations to address climate change and promote renewable energy can lead to global initiatives that harness the sun's potential for the benefit of all. Furthermore, the role of international organizations, research institutions, and non-governmental organizations is pivotal in advancing solar research and promoting equitable access to solar technology. Partnerships between the public and private sectors can drive innovation, increase investment in renewable energy, and facilitate knowledge sharing across borders. By working together, we can accelerate the transition to a solar-powered future and build a more sustainable world. As we reflect on the sun's significance, it is clear that it is not merely a source of light and heat. It is a fundamental force that shapes our existence and influences our future. The sun's energy is the foundation upon which life thrives, driving ecosystems and powering the technologies that enhance our lives. Understanding the sun's complexities and embracing its potential will be key to addressing the challenges of our time and ensuring a sustainable and prosperous future. The journey of discovery and exploration of the sun is far from over. As we look ahead, we must continue to seek knowledge, foster curiosity, and cultivate a sense of wonder about the universe. The sun, in all its brilliance, will remain a beacon of inspiration, guiding us on our quest to explore, understand, and protect our world and beyond. Through collaboration, innovation, and a commitment to sustainability, we can harness the power of the sun to illuminate the path toward a brighter and more equitable future for all. In summary, the sun's role in our lives is profound, multifaceted, and ever-evolving. From its historical significance and cultural impact to its scientific mysteries and technological applications, the sun shapes every aspect of our existence. As we navigate the challenges of climate change and resource depletion, our relationship with the sun will guide our path towards sustainability, innovation, and exploration. By embracing the lessons of the past and envisioning a future powered by the sun, we can create a world that thrives in harmony with the natural rhythms of the universe. As we move forward in our exploration of the sun, it's crucial to address the intricate relationship between solar activity and Earth's environment, which has profound implications for both our technological systems and our climate. The sun is not merely a distant star. It actively influences our planet in ways that can be both beneficial and detrimental. Solar activity, including phenomena such as solar flares and coronal mass ejections, CMEs, can disrupt communication systems, affect satellites, and even lead to power outages. Solar flares are intense bursts of radiation resulting from the release of magnetic energy associated with sunspots. These flares can emit high-energy particles and electromagnetic radiation across the spectrum, impacting Earth's magnetosphere and atmosphere. When a flare occurs, it can enhance the auroras, creating stunning displays of light in the polar regions. However, these energetic particles can also pose risks to astronauts in space and affect the functionality of satellites and communication systems on Earth. Coronal mass ejections, on the other hand, involve the expulsion of large quantities of plasma and magnetic fields from the sun's corona. These events can propel massive bursts of solar material towards Earth at high speeds, potentially causing geomagnetic storms when they collide with our planet's magnetic field. Such storms can lead to disruptions in satellite operations, navigation systems, and power grids, posing challenges to modern infrastructure. Understanding and predicting these solar phenomena are critical for mitigating their impacts on technology and society. To address these challenges, scientists employ a variety of tools and techniques for space weather forecasting. Satellite missions equipped with advanced sensors monitor solar activity and collect data on solar wind, magnetic fields, and radiation levels. This information is analyzed to produce forecasts and warnings for potential solar events that could impact Earth. The integration of real-time data with predictive models allows for timely alerts that can help protect critical infrastructure and enhance public safety. The study of solar-terrestrial interactions also has significant implications for climate science. While the sun is the primary driver of Earth's climate, the complex interplay between solar activity and climate patterns is still a subject of ongoing research. Variations in solar output, particularly over extended periods, can influence climate trends, including changes in temperature and precipitation patterns. Conversely, periods of increased solar activity, such as the medieval warm period, have been associated with warmer climate conditions. However, establishing a direct causal relationship between solar cycles and climate variability is complex and requires careful consideration of multiple factors, including greenhouse gas concentrations, ocean currents, and atmospheric dynamics. The interaction of these variables underscores the need for a holistic approach to understanding climate change and its drivers. In recent years, the urgency of addressing climate change has intensified discussions about renewable energy sources, particularly solar energy. The transition to solar power offers a sustainable alternative to fossil fuels, enabling us to reduce greenhouse gas emissions and combat climate change. The scalability of solar technology, coupled with advancements in energy storage and grid integration, positions solar energy as a cornerstone of a sustainable energy future. Investing in solar energy infrastructure not only has environmental benefits, but also economic advantages. The solar industry has experienced exponential growth, creating jobs in manufacturing, installation, and maintenance. Transitioning to a clean energy economy can stimulate innovation and drive economic development, particularly in regions that have historically relied on fossil fuel industries. By fostering a robust solar sector, we can enhance energy security, create local jobs, and promote energy independence. Moreover, the democratization of solar energy through community solar projects and decentralized energy systems allows for greater access to clean energy, particularly in underserved communities. By enabling individuals and communities to harness the power of the sun, we can empower people to take control of their energy future and reduce reliance on traditional energy sources. This shift toward distributed energy generation can also enhance resilience, particularly in the face of natural disasters and climate-related disruptions. As we consider the future of solar energy, we must also acknowledge the ongoing advancements in solar technology and research. Innovations in photovoltaic materials, such as perovskite solar cells, promise to enhance efficiency and reduce costs, making solar power more accessible. Research into solar energy storage solutions, including advanced battery technologies, will be critical for addressing the intermittency of solar power and ensuring a stable energy supply. In addition to traditional photovoltaic systems, the integration of solar technology into building designs, known as Building Integrated Photovoltaics, BIPV, is gaining traction. BIPV systems allow buildings to generate their own electricity while serving as functional components of the structure. This approach not only maximizes land use but also enhances energy efficiency, contributing to the overall sustainability of urban environments. Furthermore, the concept of solar farming, large-scale solar installations designed to generate electricity for the grid, continues to gain popularity. Solar farms can be established on land that is unsuitable for agriculture, allowing for the dual use of land resources. These farms can significantly contribute to meeting energy demands while minimizing land use conflicts. As we explore the broader implications of solar energy, it's essential to highlight the role of education and public engagement in fostering a culture of sustainability. Raising awareness about the benefits of solar energy and its potential to combat climate change can drive grassroots movements and encourage community involvement in renewable energy initiatives. Educational programs that promote solar technology and sustainability can inspire the next generation of scientists, engineers, and advocates for a cleaner, greener future. Engaging communities in discussions about solar energy and climate action can empower individuals to make informed choices and advocate for policies that promote sustainability. By fostering a sense of shared responsibility and collective action, we can build a stronger movement toward a solar-powered future that prioritizes equity, accessibility, and environmental stewardship. In addition to addressing climate change, the continued exploration of the sun's mysteries has the potential to unveil groundbreaking discoveries that can reshape our understanding of the universe. As technology advances, the capabilities to study the sun and other celestial bodies will expand, opening new frontiers for exploration. The James Webb Space Telescope and other future missions are set to provide unprecedented insights into stellar formation, planetary systems, and the intricate workings of the cosmos. The quest for knowledge about the sun and its role in the universe is not merely an academic pursuit. It has practical implications for humanity's survival and well-being. The insights gained from solar research can inform strategies for addressing pressing global challenges, from energy security and climate change to health and technological innovation. By recognizing the interconnectedness of these issues, we can develop comprehensive approaches that leverage the sun's potential for the benefit of all. In conclusion, the sun remains a constant source of fascination, inspiration, and discovery. Its influence on our planet and its profound implications for our future are undeniable. As we navigate the challenges of the 21st century, embracing the sun's power and exploring its mysteries will be essential for building a sustainable, resilient, and equitable world. By harnessing solar energy, advancing scientific research, and fostering a culture of sustainability, we can illuminate the path toward a brighter future, one that honors the legacy of the sun and ensures its vital role in supporting life for generations to come. The journey of understanding the sun is far from complete, and as we look to the future, the opportunities for exploration and discovery are limitless. We must continue to push the boundaries of our knowledge, harnessing the power of innovation and collaboration to unlock the secrets of the cosmos. The sun, in all its glory, serves as a reminder of our connection to the universe and the shared responsibility we have to protect and preserve the delicate balance of life on Earth. As we move forward, let us embrace the lessons of the sun and commit ourselves to a future powered by knowledge, creativity, and sustainable practices. In this context, the ongoing exploration of solar phenomena, advancements in renewable energy technology, and the quest for sustainable solutions will shape the narrative of our relationship with the sun. By prioritizing research, investment, and community engagement, we can foster a deeper understanding of the sun's role in our lives and its potential to drive positive change. As we celebrate the beauty and complexity of the sun, let us remain dedicated to safeguarding our planet and embracing the opportunities that lie ahead. Through our continued efforts, we can ensure that the sun remains a guiding force in our lives, illuminating the way toward a more sustainable and harmonious future. The exploration of the sun is not just a scientific endeavor, it is a journey of discovery that transcends disciplines, cultures, and generations. Together, we can harness its energy, unveil its mysteries, and honor its significance as the heart of our solar system. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.